we're looking at something called a Stokes law. So before I talk about it, I want to ask you guys a commonsensical question. I have a scenario wherein I have two similar objects, same mass, same structure and all of that, dropping from the same height. Who will reach the bottom, say to this level? Let me take this level actually. It will make more sense. Say who will pass this line faster? Who will pass this line faster? B, right? So can I tell this particular object will fall slower? So now my question to you guys is why? Because yes, along the path we have a liquid. So what? Well, liquid will provide the opposing force to the movement. Do you guys agree? So what is this force equal to? What is the value of this force? Well, we have two actually. So one of it is what? We have buoyant force, and we have one more force that is because of viscous drag. And this value for a particular set of conditions applied, is given by Stokes' law, guys. Okay. See, it's quite simple. Whenever you are making something fall, say through water, and say I compare it with honey. Say I have a bottle with honey. Honey I think will be the best thing to compare with. So yeah. So now who will fall faster? Who will be slower? B will be slower. Do you guys agree? If this is water and this is honey, B will be slower. Why will B be slower? Because honey, one thing is it's more denser and it's more stickier. So stickiness is also a factor. Do you guys agree? Stickiness also is a factor. So stickiness also opposes something flowing through a given liquid. Do you guys agree? And that's what we are trying to take into account. Okay. And that's what we are trying to take into account. And that we are doing with, and that is done by this particular formula. That value is given by this particular formula, and that formula is your Stokes law. Of course, there are certain condition that is applied, and what is that condition? We'll be looking at that. So Stokes law gives us the viscous drag. What is viscous drag? Viscous drag is the opposing force exerted by a fluid on an object moving through it due to internal friction. So drag, you guys, I hope you guys remember drag. You guys had drag before whenever you have an object falling, terminal velocity and all of that. I think you have seen. Some of you might have seen. Some of the syllabus has that. So not everyone has that. Anyways, between adjacent fluid layer. So Stokes' law gives the viscous drag, this internal resistance experienced by a small spherical object moving slowly through a viscous fluid at a very low Reynolds number, where Re is less than 1. So one small note, you have seen Reynolds number being less than 2000 and all of that, but here it's less than 1. So what is this set of value? What does it mean? I'll be giving you guys a small note to understand this. Okay guys, so Stokes' law is a simple law which gives you guys a formula for a particular scenario. That's all you guys have to keep in note. And that particular scenario being an spherical object falling through a fluid. So what is the cause of this drag force? Let's understand that first. That's more important. See, first thing is, you can use this diagram also to understand. So you have an object. By mistake I drew a rod, but anyways, this is true even for a rod. You have a small rod falling through it. What happens? As soon as it gets in touch, slowly it's falling. First thing, the molecule gets stuck. Help me, we are stuck. Now, as and when it falls, what happens? There are layers of liquid that will follow it. the layer which is close to the object will be falling faster than the layers which are further away. Very far away will not be able to feel this. Okay, with all of these conditions and everything, we are using this formula. Okay, guys. So basically, we have viscous drag. So this leads to viscous drag. I hope you guys remember viscous drag concept. We have been using that from start of this particular section. The fluid layer is in contact with the sphere moves with the sphere's velocity. This set of molecules and everything. Layers further away remains almost stationary. So as and when you move away, it becomes more stationary. Hence, a velocity gradient exists between the surface of the sphere and the stationary fluid. And this leads to what? This leads to a gradient. This causes shear viscous force, which opposes motion. Okay, yes, that's the cause of the drag. Because there is internal friction, right? I hope you guys, again, oh yeah, small note. If you're not done sequentially, all of these videos are not sequential, you'll not be able to understand the advanced concept. This is an advanced concept. Okay, for your grade, it's an advanced concept. Now, official statement is that, the Stokes law's official statement is that, for a small sphere of radius r, moving through a uniform velocity v, through a fluid of viscosity eta, the viscous drag force is given by this particular formula. Okay, as simple as that. Is the law valid all the time? The formula applies only when a set of conditions. What are those conditions? The fluid extends infinitely, so no wall effect. Basically, compared to the object, the fluid is in a huge container. Okay, so basically the last most particle just before the wall. Okay, yes. The particle before that will not be experiencing or will not even notice that this is falling through. So the velocity of particles just before the wall per se is 0. I don't know if you guys understood that. If not, you have to work on your basics. So basically, there's a lot of fluid compared to the object. The sphere is rigid. I hope you guys know the definition of rigid. Smooth and spherical. No slip occurs at the sphere surface. So things get stuck and move along with it. Flow is laminar. I hope you guys understand the word laminar. Spherical size is much, much bigger than the molecular spacing. Okay, so with all of this condition, we'll be able to use that particular formula. So it looks too vague. Is it actually useful? It is actually. Let's look at the application. So I think this is what I like. Motion of raindrop and dust particle in air. This is something that we observe, right? So for these scenarios, we'll be able to apply Stokes law. So you can read the other remaining ones. Okay, so all of those cases we'll be able to apply Stokes law. A small note on your Reynolds number. See, I happen to use 2000 sometime, and in this video we are using 1. So what is this? Well, Reynolds number, if I are using the range of 0 to 2000 and all of the set of numbers, we are talking about a fluid flowing through a pipe per se. So when we are talking about such range, we are talking about an external object passing through the fluid, or the fluid going around an external object. Okay, so this is to do with internal stuff. This is to do with when another object is flowing through it. So a small difference you guys keep in mind. Now it's for me to tell you guys when to use what. So with in numericals and with MCQs, you guys will get to use it properly, and yeah, then it will make more sense. For now, you keep all of this in mind. I'll be deriving the Stokes law formula in the next video. For now, you guys can just have a look, get a feel of it, think over it, then we'll be deriving it.